Welcome to this week's episode of the Structural Engineering Podcast. Today we're talking with Thor Madison, a structural engineer in California and the inventor of skinny braces. What are skinny braces? Picture a cantilever column system with a special fuse that allows the designer to use an R of 6.5. Skinny braces are specifically designed for tight retrofits of soft story structures, but are permitted for new construction as well. Check out their website at quakebracing.com to learn more. Now let's chat with Thor.
Right. I am a structural engineer based in Berkeley currently, and I've been specializing for about the last 10 years in crawling under people's houses and telling them how to keep them from falling down during the impending earthquake.
And is your firm your own firm? It is. You own it?
Well, it's me and currently two other people who were scattered to the winds during the COVID-19 shutdown and isolation.
So Brian and Alex over at Bay City Construction reached out to us and said, we have to interview you and we have to get to know you. And so we jumped on a phone call and talked a little bit. And the thing that they were really excited about and why we have you here today is to go through and discuss the skinny brace. Could you tell us a little bit about what the skinny brace is and what it's used for?
Sure. The skinny brace is a system that I developed that is meant to increase the ductility of what might be looked at as a cantilevered column system for bracing existing soft story buildings. The benefit of it is it provides enough ductility that you can use the same seismic response factor as you would for plywood shear walls. So instead of using an R of 2.5 or less for a cantilever column, you can now use an R of 6.5. So that gives you a tremendous benefit on reducing the structural forces in the system.
That was something I thought was really cool when we spoke the first time, was that you're taking the system that people are used to installing and you're increasing the ductility of it to make it more beneficial to the homeowner, really, at the end of the day. So how did you come up with this idea?
I started working on earthquake retrofits about 10 years ago, and at that time, we were just coming out of the previous recession, and nobody really had a lot of extra money to spend on a retrofit. So if you went in with a steel frame into most of the buildings in San Francisco, you open up the garage door that needs the reinforcing, and you see on one side of the garage, there's a gas meter. On the other side of the garage, there's an electrical panel. And across the ceiling, you've got a bunch of ducts and conduits and pipes and dryer ducts and things like that. And putting in a frame, it just means that you need to go up one side of the garage, across the ceiling, and down the other side of the garage. And there's just obstructions everywhere. So frames were really kind of out of the question. So at that point, you're looking at a cantilever column system. And the R factor that you have to use for even a special cantilever column just kind of kills you. At that time, you needed to use the lowest R factor that was applied to any direction of the building for the entire structural system. So now, even if you have a plywood shear wall at the back of the garage, you need to design that with an R factor of 2.5, which again, that just annihilates any hope of getting enough plywood across the back of the garage. Thankfully, that requirement has been lifted for most of the jurisdictions that I work in. They've got local amendments saying that you don't need to use the lowest R factor for one particular direction. Even so, once you start using R of 2.5 for the cantilever column, you've got a pretty enormous footing that you need to dig. In one case, the contractor had to pay more to dispose of the spoil from the excavation than the actual steel column cost. So that's one of those hidden costs that most engineers don't think about. But when you're in a city like San Francisco and there's nowhere to take a pile of dirt,
Can't throw your dirt over the hill.
Start another island out in the bay. Okay, so I might have lost track of what the question was.
Sorry.
Where are we going?
I gotcha.
Well, no, I think that was kind of the introduction to it. For people that haven't, we'll put some links to your website and try to get a photo in our show notes and whatnot. But could you kind of describe what it looks like if you've never seen this?
All right. So the skinny brace is essentially some specially cut structural fuses that are mounted on the top of a column, and they sort of interface between the column, which is a wide flange section embedded in or connected to a new foundation, and the existing structure up above, assuming you're putting it into an existing building. The structural fuses are meant to absorb the seismic energy and dissipate all the earthquake energy through yielding of that specially shaped piece of steel, or actually two pieces of steel that are sandwiching the web of the column. So you're going to see a standard wide flange with a couple of strangely shaped pieces of steel bolted near the top and connecting to a sliding connection that is then attached to the wood framing of the building.
From looking at the photos, the first thing that came to me was like a grandfather clock or something. It's the fuse is kind of a big pendulum almost looking, and they're really cool looking systems. So I'll definitely throw a photo in there. So I guess the question I have for you is, as a practicing engineer, what was the process like to develop a system? Did the skills that you have as a design engineer transfer over to? Is it similar at all? It feels more like a mechanical engineering task, almost, to get down to those minute details.
There was a lot more mechanical engineering skills, or I assume skills that I had to apply. Not being a mechanical engineer, I don't really know what they do. I had to think a lot about how things were going to interface with each other when there was significant movement in the system, because I was looking at drifts of maybe up to 5 inches or so between the wood framing that I'm trying to brace and the top of my column that I needed to assume was going to be in a fixed position relative to that wood framing. So there are a lot of arcs and sliding connections and things like that. So, and the structural fuse itself is changing to where you're considering a straight line, and then the chord of a circle when the thing starts to yield and bend significantly. So there are a lot of slots and things that need to accommodate movement. So that became quite a lot of fun. I also discovered things like friction while I was doing the testing and how that can kind of mess you up.
Working through development of it through the testing, from the conception of the idea, and it sounds like you're talking about the idea kind of came up because of what occurred with having to reduce your R value and having a lot of mechanical plumbing and items in the area. How long did it take you to come up with the system? I guess from conception to now being implemented.
So I was trying to remember when I came up with the initial concept of providing more ductility between the new structural elements, being the steel column and the existing wood framing. And at some point, I got put in touch with Chai-Ming Wang at UCSD, who's been doing steel research for decades now. And I spoke with him, and he said, well, if you're going to get a higher R factor, you've got to have a lot more ductility than just a stupid steel column that's going to bend at the base. So, which is the special cantilever column, we know where it's going to fail is at the point of maximum moment. So at the base of the column is where you get your failure. And I was trying to come up with ways that I could force the system to fail at a predictable point. So, coming up with layers of sheet steel or something like that. So actually in 2014, I patented what was essentially a hole in a hot rolled channel and that didn't work for reasons. So it didn't work because the story drift accommodation was not great enough. If you look at the pre-qualified connections for moment frames, you need to accommodate a story drift of 4%. Essentially, that's so 0.04 radians of rotation at that joint. And I wasn't getting that before the channel failed, so the channel being my structural fuse. So I kind of gave up on that, worked for, just crawling under people's houses for another year, and then realized that I really needed to finish up this idea. And so that's when, basically, one night during Christmas vacation, lying awake in the wee hours in the morning, came up with the concept as it is now, and then various refinements of that. The invention process was kind of like one day after things percolate for a year or two.
I imagine that tends to be how it happens. You just think about it in the back of your head for a long time, and it all kind of comes together quicker than you would think.
Yeah, and I keep refining it because I'm trying to think of ways that I could adapt it to retrofitting pre-Northridge steel structures or other things like that, or even creating a frame system that could be used in new construction where it would incorporate the same structural fuse concept and action.
How did you get to the fuse shape that you have now? It's not quite parabolic, but it has a slight curvature coming down to its hinge point. How did you refine down to that shape?
So that essentially you're looking at if you look at the statics of the way the thing is loaded, it's really just a beam on two supports with load at a cantilevered end. And so
the moment diagram of that.
Yeah, and you have to turn it 90 degrees because it's vertical, so that throws some people off. But you look at it, and the point of maximum moment is at the top of the column. And then at the bottom of the fuse, if we're looking at it as it's oriented in nature, the moment is zero. So you've got a linear, let me back up. The moment increases linearly from the bottom of the fuse to the connection point at the top of the column. And so I wanted ideally to have the section modulus increase linearly so that yielding would essentially occur simultaneously along the length of the fuse.
Mm-hmm.
So friction turned out to kind of foil that, but that was just sort of a minor hiccup. So to increase the section modulus linearly, since the section modulus is based on the depth of the section, the square of the depth of the section, I needed to increase the width according to a parabolic formula. So it is actually a parabola.
It is, okay.
But on top of that, since friction was messing things up in the initial testing, I wanted to have the failure occur closer to the bottom of the fuse. And so instead of having yielding occur simultaneously along the length of the structural fuse, I wanted to have a safety factor. So yielding begins at the very thin end, the tail end of the fuse. And at that same time, I've got like a 33% factor of safety, if you want to call it that, at the wider point of the fuse.
Mm-hmm.
So there's that additional factor that goes into determining what the width of the fuse needs to be at any point along its length.
When you're looking at this after a seismic event, what does the evaluation of it look like?
If you're looking at a piece of steel and you saw that the paint had flaked off of it, or mill scale had flaked off of it, or there's obvious cracking, you know you've got some serious distress of that member. I didn't really want to trust, somebody who's not trained in that kind of inspection to go out and make a call on whether the steel is fatigued too much.
Mm-hmm.
One thing that came in during the development of the system is that it needs to have some shear pins in it. So there are a couple of small bolts, at least 2 small bolts that go through the structural fuses and also the web of the column or the sliding T at the top. So if either of those has been sheared through, then it's just time to go ahead and replace the structural fuses and install new shear bolts. And that is extremely conservative because
Mm-hmm.
those shear off at the very beginning of the loading history during testing.
Mm-hmm.
And we got dozens of cycles back and forth of greatly increasing deflection. So there's plenty of reserve capacity after that.
Yeah. Are the fuses designed to be replaced after an event? Can they just be swapped in and the column remain in place?
That is a big part of the plan. So, barring any other distress of the column itself, the column and all the connections, and we hope the foundation, which is designed by the design professional, should fail well after the structural fuse has failed. So, it's designed to for the structural fuse to take all the deformation and provide that. I'm trying to remember the term that the steel people use, and it's going to come to me when we hang up. So, dedicated energy dissipating mechanism or something like that. The structural fuses should be the only thing that deforms inelastically in the whole system. And it's very easy to design it that way and force it to yield before anything else does.
We've talked a lot with the system being used for existing structures and retrofits. Can it be used in new construction? And if so, would it be the traditional steps of going through ASC 7?
It can certainly be used in new construction. And really the analysis, you just go ahead and do your analysis based on an R of 6.5, and the evaluation report allows substituting the skinny brace for any wood structural panel shear wall system. So you can just take out the shear walls and put in a skinny brace and carry forward as you would with any other design. So it's similar. The approach is similar to any sort of prefabricated shear wall system that the various big name manufacturers make. So you go in and you determine your forces based on the seismic design coefficients that are given in their evaluation report, and then go choose whichever system meets the strength requirements for that particular building.
Okay, yeah, that makes sense, and it kind of leads into the next question about the approach that was in the report that you're discussing, that said that it was evaluated based off of the more of a shear wall testing kind of parameters. So that makes sense. I think that was the approach taken because it's more or less a one-for-one kind of system.
It was a challenge figuring out exactly how to test it because it's not a frame, right? So I can't, there's no joint that I'm really testing. And it's obviously not a plywood shear wall. So I really just kind of thought, okay, I'm looking at mimicking behavior of a plywood shear wall. And if I can, because I want to, the biggest use of this thing that I saw was going into wood framed structures where the rest of the bracing was going to be done using wood structural panels. I keep saying plywood because that's the only thing that we really trust out here in the Bay Area. So getting the system tested in accordance with the same rules that apply to the wood structural panel shear walls or the substitutes for those. That seemed to make sense, and I was, I expected that it would satisfy the evaluation agencies and thence the building departments. That was mostly true. The whole evaluation process is really pretty opaque. So there are a lot of these documents, like the one that you were asking about. I'm not even sure if I'd be able to see that document. The ICC Evaluation Service and IAPMO Universal Evaluation or Uniform Evaluation Service, they have their own, actually they're engaged, or at least more recently, they were engaged in a copyright battle over who got to use which evaluation criteria, and the very term evaluation criteria, I think, is probably trademarked by ICCES, and so I probably shouldn't use it on this podcast.
We can
So, fortunately for me, somebody had the sense to go to ASTM and basically duplicate one of those proprietary evaluation documents. So ASTM D7989 is essentially a clone of one of the ICC Evaluation Services procedures for evaluating plywood shear walls and things that you want to act like plywood shear walls. So that's what we used.
To act like a shear wall, do you have to have compatible or similar strain characteristics? Like, does the deflection have to match, or can you just, in your calculations, determine the stiffness of the skinny brace and the stiffness of the walls you have and figure out where your load's going to go?
The requirements for the deflection, that's actually why we needed to add the shear bolts that I mentioned earlier.
Mm-hmm.
Because, the steel is nice and flexible and ductile, but the requirements for the evaluation report were that we had something that was pretty stiff to begin with. You're really trying to imitate a perfectly elastic plastic material where you have fairly stiff behavior, and then you can reach a certain point and it just yields forever.
Yeah.
The exact requirements for the rated capacity of the skinny brace is that you take your drift amplification coefficient, so CCD of 4 for wood structural panel shear walls. You take your allowable story drift of 2.5%, and you divide the story drift by 4, and you come up with essentially the tested or the elastic value of your drift is 0.625%.
Mm-hmm.
So whatever load produces 0.625% drift, that's the maximum load that is allowed for ASD load rating for that skinny brace. For me, it was kind of bad timing for me to invent this thing when I did, because the 2015 IBC required they dropped Chapter 34, which was the existing building provisions, and they now put in a requirement saying that any new seismic components, even if they're installed voluntarily, they need to meet the criteria for new construction. So that meant that you could no longer just put in something and say, well, we're making the structure better.
Mm-hmm.
You actually had to show that you were meeting requirements for new construction. So generally that was taken by building departments to say, okay, you need to have an evaluation report for this thing. You can't just say this is a really cool system and we did some tests on it, didn't fail. So you have to have the evaluation report. And so for me, I'm looking at requirements that apply to new construction and an evaluation procedure that's used for components going into new buildings. and I'm putting these things into 100-year-old buildings that have probably already swayed back and forth in that 0.625 story drift that we were talking about earlier.
Yep.
So it's a bit of an onerous requirement for existing construction, in my opinion, especially when the homeowners really don't care if their plaster cracks a little bit in the garage or the basement where this thing is usually going. But that's what we're dealing with. And at least now, if I want to sell them for going into new construction, they meet those requirements.
Yeah.
So you can use them if you want to have only 9 inches of solid wall and the wall of your house facing the great view that you want to have.
I think a lot of architects might take you up on that. How are you collecting force into this? I know you have some diagrams on your website. Is this installed in between joists and then you reinforce those joists as needed and then reinforce the diaphragm above as needed? And what does that interface look like between the skinny brace and those joists?
So that's actually one of the great advantages of the skinny brace is using the R of 6.5. It's really pretty unusual that you need to reinforce the diaphragm connections to the joists at all. And typically, if we're looking at a house in San Francisco or a typical, like a master bedroom suite above a garage or something like that, the joists are often, they go the full width of the building. So by connecting to a pair of joists, which is one of the options, you drop the skinny brace down between, you drop the skinny brace into the center of the joist bay, and we've got the brackets that connect directly to the joists. So now you've got a pair of joists that you're connected to. And if they're going across the full width of the building, typically you don't need to reinforce the connections to the diaphragm at all along that. In San Francisco, probably about half the time you've got full width joists. So 25-foot long lumber was commonly available when they were doing their construction. In the cases when you don't, there's a splice across the center beam that runs the length of the building, and you just reinforce those connections at the lap splice as you would, however it's appropriate. But that's up to the design engineer. We did have, I gave a seminar introducing the product to some engineers one time, and there was one guy who just really was uncomfortable with that. He said, well, it'd be better to have 2 skinny braces. And I said, well, I'm very glad to sell you 2 of them, but you only need 1. So
if you're in San Francisco, if someone outside of San Francisco wanted to buy the product, do you sell it as the whole system? Do you allow other manufacturers to cut out the fuse portions, or do you mail the fuse basically and you can add that to any column?
So that was one of the frustrating points for me going through the evaluation process, because the secret sauce really is the structural fuse and some of the related pieces that go on to the top of a column.
Mm-hmm.
So unfortunately, all those connections and the hole sizes in the column need to be part of the quality control process that is goes into approving the entire system.
Mm-hmm.
So I would much rather be able to throw 200 pounds of steel into a couple of boxes that FedEx can deliver, but now I have to add a stupid 10-foot long piece of W8 by 35 or heavier. So now we're shipping at least 400 pounds of steel, maybe as much as 1,400 pounds, and it is kind of annoying to when we expand. We'll need to have approved fabricators that can be assembling these things, perhaps in Portland or Seattle or LA.
Mm-hmm.
But right now, the only approved manufacturer is in the Bay Area, so they all need to come from the Bay Area.
I'm going to cut out some stuff here. For the next 10 minutes, Thor and I talked about finished surfaces of cuts and how the cuts have to be made specifically, whether that's by laser or water jet. Although it's fun to talk about, it's probably deathly boring to listen to. So let's just sum up this real quick. Does Thor have to do anything specific? Yes, he does, but testing every possibility in even the worst finished surface, Thor was able to get the performance that he needed. So from FEMA 358, the requirements for finishing of an RBS connection, which is probably what this is most similar to as far as the finished surface, dog bone cuts have to be smooth to 500 microinches. Thor said he had some surfaces that were 100 times rougher than this and still went beyond the necessary requirements.
Best one where we kept going until the wood floor framing mock-up just sort of splintered and fell apart. We got 42 cycles beyond 4% drift, 12 cycles between 6 and 8% drift, and then 2 cycles beyond 8% drift.
As we said before, 4% drift is a lot. 42 cycles past 4% drift would just tear a house apart. Great that the system can do that, and that's something that makes the system really cool. It truly just soaks up energy without too much degradation.
So if you want something that's ductile, this system provides it.
How many skinny braces have been installed so far?
We're in the range of dozens at this point. Without the COVID interruption to regular life, I think we'd probably be at the end of the year, we'd be into the hundreds or so.
All right, to wrap it up, we've asked everybody that has, years of experience, and you have many years of experience. What would you say is like a good top 3 tips for a new engineer?
I might need to give you 4, but I'll start with 3. The first one, I started out working my way through college for 12 years, so that was to get a bachelor's. I was not in college all that time, but I was out building stuff or doing construction, and that was probably more valuable than anything else to me as a practicing engineer, especially doing primarily wood frame construction. So get out and build stuff, either for Habitat for Humanity or Rebuilding Together. The Rebuilding Together organization has chapters, I think, throughout the country also, in addition to Habitat for Humanity. So that's a big one. Also, joining professional societies will put you in touch with people that you will benefit from, and it'll kind of open up paths that you never even knew existed. That's actually how I got in touch with some of the people that helped me out with this system. I volunteered helping out the city of San Francisco developing some of their retrofit standards. And next thing I know, the guy that was helping me with that put me in touch with Charlie Kircher, who was the head of the committee that developed FEMA P795. So, that was a great connection to spend a couple of hours with this wizard in steel design without having to pay him. So that was really beneficial. And I guess, just thinking outside the box, engineers coming into practice now are going to be facing some pretty incredible changes over their careers. And it's probably going to take some really creative thinking to do that. So try to stray away from the standard designs and do use some crazy new techniques or materials or methods, or whether it's skinny braces or something else.
Perfect. And you said you had maybe a 4th one to slide in there?
Yeah, I guess the other one is kind of more of a business approach.
Nice.
And I kind of learned this lesson the hard way after being in a meeting with a client. listen to what your client wants and do your best to make that work. So rather than giving a list of reasons why you can't do something, sort of turn the tables and say, well, yeah, we could make that work. We just need to do X and Y. And so, you need to act like you're on the side of the client rather than acting like you're on the side of the building code or some unseen legal battle that you fear you might get embroiled in if you do something new and creative.
Uh-huh. I think that's very good advice. Well, cool. Thank you, Thor. I think this system is really, really nifty, and I think it's got a good future to it. I guess there's not a lot of soft story out in Salt Lake, but there's a lot of retrofit work that needs to be done. So you should come on out here too.
Well, yeah, I'd love to come out for a visit when we can travel anywhere easily.
Who knows when that will be, but I'll look forward to it. Yeah, thank you very much for coming on and taking over an hour out of your day to talk with us.